Okay, today we're going to talk about polar coordinates. We are pretty much done with all of the very trigonometry focused basics, and the remaining topics for this semester, all the stuff in Chapter 7, are going to be some things that are going to be related to trigonometric topics. We'll see sine and cosine again in this very section, for example. But these are really topics that are going to be useful things throughout calculus and beyond. So these aren't necessarily directly tied to trigonometry, but they're all going to be certainly at least tangentially tied to trigonometry. So polar coordinates are going to be a new coordinate system. And so what is a coordinate system? Well, we've been using a coordinate system for this entire semester. We've been using the xy plane. So the Cartesian coordinate system is the one that we're used to. The Cartesian, here we go. Cartesian coordinate system is the xy plane. That's what we normally think about. This is the one that we're used to using. That's called the Cartesian coordinate system. It was named after René Descartes, the famous I think therefore I am guy. And he invented basically this idea of giving a reference point to locate sort of these mathematical ideas in space. And his idea was this Cartesian coordinate system. The Cartesian coordinate system, it uses two distances to specify a location. Right, so this is the idea. It uses two distances to specify a location, the x, so how far we go horizontally, comma the y, how far we go vertically. And this is pretty intuitive to us now because we've probably been using the Cartesian coordinate system since like middle school. We are going to be using a new coordinate system called the polar coordinate system. The polar coordinate system will use two new variables. Instead of x and y, we will use r and theta. R is going to be a distance, just like x and y kind of are distances, and theta is going to be an angle. So in this case, we use one distance, r, and one angle. That's going to be theta. We'll typically list the coordinates in the same way as sort of an ordered pair. So we'll identify a location. Identify a location using the same type of ordered pair. And it'll be r first and theta second. Okay, so this is all fine and dandy in the abstract, but to have this actually make sense, we should draw a picture. And so let me draw kind of both of these things together. I'm going to start with a Cartesian coordinate system that looks like this. So here's my vertical line, my y-axis, here's my horizontal line, my x-axis. So here's x. Here is y. And maybe this is the point I'm interested in right here. This is the point we can call P. In addition, I will call this point O for the origin. Normally, the coordinates of this point would just be however far we need to go in the x direction. So let me draw in a little triangle here. We would go this far in the x direction, this far in the y direction, so I'd call this x, this y, and that's what gives me the coordinate xy for that particular point. In the Cartesian coordinate system, we're going to measure our distance in a straight line to the point, and we're going to call that our distance r. And this angle is going to be the angle that we use to identify that same point. So we can identify this point as xy, or by its coordinates in polar coordinates r comma theta. So r comma theta. So again, we're basically giving a distance and a direction now. So our distance is r, and it's basically the distance from the origin to the point. So it's the length from origin to the point P. And then we also have a direction. That's our theta. And it is the angle from basically the positive x-axis measured up to P. So this is how we're going to deal with our new coordinate system. So I want to tie this now to trigonometry. Why are we learning this in a trigonometry class? Let me erase the bottom of this graph so I don't waste space. I'll just, while I'm at it, erase a little bit over here so that our picture doesn't take up so much space. How does this relate to trigonometry? So we already said that we can identify that point in either of these two ways up here in the corner here. We could call the point P either x comma y or r comma theta. And so I want to take a look at sort of this picture we've drawn, because if we look at the picture, what we've really got is a right triangle. And if we kind of zoom in on that, this is what our triangle winds up looking like. So I want to take that triangle down here. Here's what that triangle looks like. There's the right angle. Here is theta. Here is r. Here's that point P. Here's where O was. This side is x, and this side is y. So there's the triangle that we've got sitting in there. And I want to think about, how are these variables related? So how are the xy coordinates related to r and theta? And with that picture, we can figure out the relationship. So I want to think about what trigonometric identities I can use to shed a little light on this. So I want to think about the relationship between y and r and theta. So for example, and also x and r and theta. So for example, I want to think about, what is the cosine of the angle theta? Looking at this triangle, if I look at the cosine of theta, and remembering our SOHCAHTOA, the cosine is going to be our adjacent over our radius, or over our hypotenuse. So in this case is x over r. I can solve that for x and find out that x is equal to r cosine of theta. We've already talked about this relationship. We've drawn this triangle a million times before, back when we talked about the unit circle. The only difference was, instead of having r here, we had a 1 here because it was a unit circle. So now we're actually treating it as an r. Do the same thing with sine. Let me give myself a little more room here. Do the same thing with sine, and we find that sine is equal to y over r, which, solving for y, gives me that y is equal to r sine of theta. And so this is going to be a really, really useful relationship. This is going to, I'll highlight both of these in just a minute and write them down. I also want to think about how I might represent, so in this case we've solved for x as a function of r and theta, and y as a function of r and theta. What if I want to solve for r or theta as a function of x and y? So what are the other relationships? So here's one set of relationships, here's another set of relationships. So for example, is there a relationship that relates only theta with x and y? And in this case the answer is yes. If I look at the tangent of theta, I get y over x. Or solving that for theta, how do I undo a tangent over here? So I've got this tangent of theta equal to y over x. How do I undo the tangent part? We need an inverse tangent. So here's my arctan, y over x. So there's what theta is equal to. It's that angle. In practice, this is not going to be a terribly useful form. We want to avoid having to use inverse trig functions, but it's there if we wind up needing it. Similarly, I want to look at a relationship that relates only x, y, and r without having to worry about theta. That way I can try to solve for r in terms of x and y. So let me do that. In this case, the relationship that relates those three sides, because it's a right triangle, it's just the Pythagorean theorem. And I know that x squared plus y squared, so here's my two sides squared, must be equal to the hypotenuse squared. And if I solve that for r, by taking the square root, I'll find that r is equal to the square root of x squared plus y squared. And that gives me a second set of relationships that I can use. So let me clean these up, get rid of all these underlines I did here. There's that one, that one, that one. And while I'm at it, let me get rid of these ones here and here, just make it a little cleaner. Here's all my important relationships. So let me highlight all of them. This one, this one, this one, and this one. Those are the relationships that are going to be really, really important. They will allow us to convert from Cartesian coordinates to polar coordinates or from polar coordinates to Cartesian coordinates. And we'll see how that works going forward. It's going to be a really useful thing, and we'll see exactly how and when it's useful. So let me do some examples. So the first examples I want to do are just basically giving you a single point and figuring out how we can plot that point. So if I give you a point in in polar coordinates, can you locate where it is in our graph? So let's start by just getting comfortable with these. So plot the point r comma theta that's given. So let's do part A. The first point I'm going to give us is maybe 2 comma pi over 4. So 2 is our value of r, pi over 4 is our angle. And if I draw my coordinates here, here's my x, here's my y. What I want to think about is, first, what is the angle? And in this case, the angle is pi over 4. That is this angle heading out straight here. Oops, try to make that a little more of a dotted line. Heading out straight here, 45-degree angle. Right, it's in that direction. And then we consider how far we're wanting to go in that direction, a distance of 2. So hypothetically, if this is sort of the scales of what we're doing here, if this is 1, this is 2, 1, 2. We would go out that same distance this direction, so there's 1 and 2, and that would put us right around here at this point. So this would be the point that we'd be interested in, where this distance right there is a distance 2. Okay, let's do a second one. Let's do it right over here. What if I tell you I want the point -1, comma 7 pi over 3? So, in this case, we're going to do the same type of thing. Let me draw my coordinate axes here. Oh, this is much better than the first time, a little straighter. So here's my x direction and my y direction. Here's my Cartesian coordinates, right, x and y, but I'm trying to plot r and theta on these Cartesian coordinates. So the first thing I need to figure out is what direction I'm going. We're going in the direction of 7 pi over 3. If you think about 7 pi over 3, we've actually gone around more than one full rotation. If we went 6 pi over 3, 6 pi over 3, if you simplify that, simplifies to 2 pi. So 6 pi over 3 would give us a full rotation. This is 7 pi over 3, which tells us we've actually gone an additional pi over 3 beyond a full rotation. So we're actually in this direction, basically, where we've gone all the way around and then some to get to our 7 pi over 3. Similarly here, I should come back and mark this one. This angle was our pi over 4. So we've actually gone 7 pi over 3, and now we need to figure out how far to go. And it's telling us we need to go -1. So if I were to go +1, we would be going off in this direction a distance of 1. Because it says we need to go a distance of -1, we actually will go in the opposite direction. So we'll go in a negative direction. And if I just say that that distance right there is 1, but we're going again in the negative, this is the positive direction, so this is the negative direction, this is where our point would wind up. So the direction tells us we're trying to go this way. Do this with the mouse pointer here, make sure you can see it. The direction tells us we're going this way, but the fact that we're going -1 in this direction means we actually wind up going this direction, a distance of 1. So that's how the negative sign, when r is negative, how it plays out. It basically tells you go the opposite direction. I think that probably gives you a sense of exactly how we're doing this. I should mention as well, it's totally possible for the value of theta to be negative, for us to just go in a clockwise direction instead of a counterclockwise direction, but I don't think that's a particularly tricky concept, so I'm going to skip that idea for now. And what I'm going to focus on instead is how do we convert between coordinate systems? Okay, so here's our next topic, converting between coordinate systems. And again, I'm just going to do this by example. So in the first example, I want to give you an xy coordinate and ask you to convert it to an r theta. So in this case, we're going from xy to r theta. So this is the idea. So if I tell you that xy is equal to 1 negative square root of 3. They're my Cartesian coordinates. I want to figure out what is r and what is theta. To do that, we can go back up to these formulas that we highlighted here. These ones down here are the ones that are going to be useful in this case because they give us theta and r in terms of y and x. And the problem I just gave us, x and y are given, and we want r and theta. So these are the formulas we'll use when we're going from x y to r theta. So coming back down here, the easiest way to do it, we can use those formulas, but I actually just like to do what we did a minute ago, draw a picture. And it makes it a little bit easier in my opinion. So I'm going to draw a quick sketch. Here's my x direction, my y direction, and we're going to the point 1. So I'll call that a distance 1 in the x direction, and negative root 3. Negative root 3 is about negative 1.7, so I'm going to say that's right about here-ish. Boop, 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 boop. Give my little sound effects here. Puts us at this point right here. So here's negative 1, and right here I'm going to call this negative square root of 3. So this is what we're looking for. I'm looking for this value of theta and that distance r right there. The theta is kind of easier to spot now. We did a ratio of 1 in the x direction. So 1 in this direction, root 3 down in this direction. Those numbers should be semi-familiar, especially if I were to divide them both by 2. And we'd gone to the point 1/2 comma negative root 3 over 2, we would probably recognize those as points on our unit circle. But I am going to get rid of those. The angle doesn't change. We've got a different radius. We're not on the unit circle, but it's that same ratio. What this tells me is the angle that we're going to in this case is, technically speaking, it's the inverse tangent of the numbers that we've got over here. Remember, it's y over x, so negative root 3 divided by 1. Negative root 3 over 1. But the easier way to figure this out, because I don't have values of inverse tangent memorized necessarily, you can obviously do it on the calculator if you'd like, but because I don't have these values memorized, the picture tells me that this is one of those points where I'm going a little less in the x direction, a little further in the y direction. That's an angle of pi over 3. We're just going clockwise instead of counterclockwise, so this is going to be negative pi over 3. There's my angle. For the radius, I just want the distance right here, and I can do that by just, again, using the Pythagorean Theorem on this right triangle that we've got right here. So it's going to be 1 squared plus negative square root of 3 squared. So in this case, we're going to take and then take the square root of that. So square root of 1 squared plus negative root 3 squared. The 1 squared is just going to be a 1. The negative square root of 3 squared is going to be a 3. That's the square root of 4, which is 2. And so in r and theta, what we find is that the corresponding r theta value is, let me give myself some room again, we find that the coordinates r theta are just 2, that's my r value, and negative pi over 3. Okay, let's do another one, but let's go the opposite direction. So for a second example of converting between coordinate systems, I want to go from r theta to xy. In a lot of ways, this is, in my opinion, the easier way to go. So if I tell you that the r theta is equal to, let's say, 4 comma pi over 4. Again, I can draw a quick sketch, and we can figure out where this is. This will at least give us a quick sanity check. So pi over 4, that's off in this direction. We're going a distance of 4, so there's my pi over 4. There's my 4. This is x. This is y. There's my point. It's clearly going to be somewhere in the first quadrant, and it's easy enough to compute. X coordinate is going to be 4 times the cosine of pi over 4, which cosine of pi over 4 is root 2 over 2. So if I multiply that by 4, I've got 4 times root 2 over 2. I can cancel these numbers, which will leave me just a 2 in that place. It gives me an x-coordinate of 2 root 2. And doing something similar for the y-coordinate, the only difference is that we're using sine instead of cosine. But in this case, pi over 4, it has the same sine and cosine value at that angle. So this is also going to be 4 times root 2 over 2 with the same cancellation, giving me the same y-coordinate. And so we wind up with our xy coordinate being equal to 2 root 2 comma 2 root 2. Easy enough. Okay, so let's keep going. We've converted individual points between coordinate systems. Now I want to actually see what it's like if we try to convert equations. Bear with me just a moment. Let me get my notes in order here. And I want to do a couple of examples. So now I want to talk about converting equations rather than single points. We're going to use, again, those same 4 formulas that we circled over here. These same 4 things are going to be the useful formulas. And we'll talk about this in just a minute. But that's what I'm going to be referencing throughout this section. Okay, so again, this is most easily done via example. So let's start with an example. Let's say I give you an equation in Cartesian coordinates and I want you to convert it to polar coordinates. So I'm going to give you the following. Let's say y equals, I don't know, 2x squared. So this is just a parabola. I want to figure out what a parabola looks like in terms of my polar coordinates r and theta. So all I need to do is replace x and y with r and theta. So that's going to be my goal. And I can do that directly. We already know what y is equal to. Looking at those formulas above, y is equal to r sine of theta. And on the other side, that 2 will just come down, and the x we know is r cosine of theta. But I don't just have x, I have x squared, so I need to square this as well. So here's what our formula looks like to begin with. Now our goal is to just kind of clean it up and simplify. So on this side, I've got r sine of theta. On this other side, we'll have 2. After I distribute the power through, we'll get r squared cosine squared of theta. And whenever possible, see if we can now try to solve for r. So get r by itself on one side of the equation, and on the other side, all the trig functions, anything involving a theta. So this is not always going to be possible, but in this particular case, we're going to be able to pull that off. So essentially, what I'm going to do is divide both sides by, we've got an r here, we've got an r squared here. I want to divide both sides by this whole r sine theta. So if I divide both sides by r sine theta, let me just again delete these underlines. I'm just trying to highlight what I'm pointing at. So let me do it with the arrow instead. I want to isolate the r by itself. So I'm going to divide both sides by this term. On this side, that'll leave me with just a, oops, let me go back to my pen. That'll leave me with a 1. And on this side, I'll have 2r squared cosine squared of theta divided by r sine of theta. We do need to just be cognizant that we divided by r sine of theta, and there are values of sine of theta that are potentially 0. So it turns out that these functions won't be valid for those particular values of theta. So for example, theta equals 0. When theta is 0, the sine of 0 is 0. We'd have a 0 in the denominator. Technically, this function would be undefined, but otherwise it's going to match the graph of this, even though it has a single point where it's undefined, will exactly match the graph of this, other than that one point. So doing this division allows me to cancel this r with one of these r's, and now my goal is to just get this r that's over here all by itself. And so that means I'm going to now multiply by sine of theta, divide by cosine squared of theta, and divide by this 2 on both sides. And we'll wind up with the r by itself on one side. So this guy I'm just copying down over here. The r I've just copied over here. And I'm going to divide by 2. So we've got on the other side a 1, but I'm going to divide by 2 cosine squared of theta. So I'm going to wind up with a 2 cosine squared of theta. And I will multiply by sine of theta. And so we get sine of theta on the top. This is what it looks like. If you want, you can try to use other trig functions, rewrite this as r equals 1/2. We've got a sine over a cosine, that's a tangent of theta. And we would also have a 1 over cosine, that's a secant of theta. So that would be another possibility. Either of these two answers would be totally fine. Okay, so that's one way we do some of these problems. Let's try one in the opposite direction. So I'm going to give you a function in r and theta and ask you to compute what that function looks like in terms of, there we go, in terms of x and y. So let me give you r squared equals sine of 2 theta. So again, our goal in this case is to replace r and theta with x and y. This is a little bit trickier. We're going to be using these two equations more wherever possible. But again, I want to avoid using this one as much as possible. I do not want to be taking trig functions of theta where I have to write theta as the inverse tangent of y over x. So I'm going to try to avoid that whenever possible. And in reality, instead, I'm going to use these two much more frequently than I'm going to use this one. So I'm going to use this one and these two whenever possible. Okay. So, here's the ones that I'm saying, just to make it totally clear, here's the ones that I want to use. Ideally, I want to write the following. I would love to deal with r squareds, because r squareds are just x squareds plus y squareds. It's that equation we had previously, but without the square root applied to it. And I would love to avoid square roots whenever possible. So I want to write this. I'm looking for r squareds, hoping r squared show up. And I also want to deal with these ones. So for example, seeing a sine of 2 theta doesn't necessarily do me much good, but if I had an r sitting in front of it, that makes life a lot better, because I would have something that looks like r followed by a trig function. It would look more like the one I'm about to write right here, r sine of theta. So these are the ones that I really want to use. And so maybe the word right isn't what I want here. I want to use these particular ones. I guess I've got my eraser. I can clean this up. So let's see. We've got this. Let me clean this up. I want to use this set of equations. So what we'll get the following, giving myself a little bit more room here. I'm going to basically do a little bit of work to try to add some extra values of r. Again, let me just copy down what we're starting with. But I'm going to actually apply a double angle formula. Just because I, again, would rather deal with the arguments of my trig functions being theta than 2 theta. I have a better understanding of what that looks like. So I'm just going to rewrite this as r squared equals sine of 2 theta is the same as 2 sine of theta cosine of theta. That's our double angle formula that you have on the sheet that I would recommend having with you as you go through these videos. So there is our double angle formula, but I don't quite have what we have written up here. I have a sine of theta, I have a cosine of theta, but I'm missing the r's. So I'm just going to force them there. I'm going to rewrite this so that I've got a 2 here with an r sine of theta and an r cosine of theta, because that'll make it really easy to immediately say, okay, this whole piece, there's my y, this whole piece, there's my x. But what I've effectively done is in going from here to here, I had to multiply by a factor of r for the sine of theta, another factor of r for the cosine of theta. I had to multiply by r squared. There were 2 r's that I added. And so I need to do the same thing on the other side. This is going to now be, instead of r squared, it's going to be an r to the 4th. And so I want to think of that r to the 4th as r squared squared. And now I really have this set up with all the pieces exactly as I want them to make a quick, easy conversion. So on this side, the r squared, we said that's x squared plus y squared. And that r squared is being squared itself, so there's another square there. That is using this formula that's just up almost off the top here. So here's what we just used, right, and going from that line to that line. And on the other side of our equal sign, I'll still have that 2. That 2 hasn't gone anywhere. But we just said r sine of theta is y, r cosine of theta is x, and I now have my function written entirely in terms of x and y. In general, it's preferable if we're not going to be able to solve this, so solve for y if possible. But oftentimes it's not going to be possible. This one's going to be a mess, and because we're going to have to take a square root if we're trying to solve for y, taking square roots, doing a bunch of stuff, this isn't going to be possible. We won't be able to solve for y. And so what we'll do is we'll leave the equation in what's called an implicit form. Basically, we'll leave it like this, although often we'll leave it in an implicit form. So implicit form, as opposed to an explicit form where we've actually effectively solved for y. So we'll leave it in an implicit form, but sometimes it's convenient to move everything to one side of the equal sign. So if you wanted to FOIL this piece out and move this piece over to the other side, we would wind up with something that looks like this. I'm just going to skip ahead and do that. Again, I'm just getting this by FOILing everything out. I'd get x to the 4th plus 2x squared y squared plus y to the 4th minus 2xy equals 0. And that might be the way that we wind up leaving this problem. I want to do some more practice with these. I'm just not sure how many more examples. I'm sure this video is getting long and you're getting a little bit tired of it. So let me just do maybe 1 or 2 more quick examples. I'm going to go through these ones a little bit faster. And then afterwards, I'll create a second video where I show you the way that you can use Desmos to help with some of this stuff. And I would highly recommend kind of getting comfortable, because we're going to be interested in knowing what the graphs of some of these polar functions look like. It's going to be a big focus in the next section. So for now, let me just do 2 more quick examples. So here's another one. I'm going to tell you r is equal to 3 cosine of theta, and I want to know what this looks like in terms of x and y. So okay, this one's actually a little bit easier than the last one. Again, the things that I'm looking for are I'm trying to find, so r by itself is okay, but I really would love to find r squareds. Cosine of theta isn't great by itself. I'd really rather have r cosine of theta. And similarly, if sine shows up anywhere, I'd really rather have r sine of theta. I'd rather have the r's in front of it, because these 3 terms are easy to convert. This one's just x squared plus y squared. This one's just x. This one's just y. So that's what we want. This one doesn't have any of those, but I really want an r here. I'd really love an extra factor of r here. If I just take this equation and multiply by an extra factor of r, I'll wind up with something that's a lot nicer. I'll wind up with r squared equals 3r cosine of theta. And r squared, we just said, is very easy. That's just going to be x squared plus y squared. And on the other side, we've got this 3 that'll come down, but I just have r cosine of theta other than that. So that's just a 3x. Doing exactly what we did before, I can rewrite this as x squared plus y squared minus 3x equals 0. You may not recognize this immediately. We'll talk about it more in the next section when we get to graphs of polar equations. It's going to be something that we're interested in, but it turns out this is the equation of a circle. That's just a little bit off center. So it's not centered at the origin. So we'll see that in the next section. That one is done. Let's do one more example. I want to do r is equal to 1 over 1 plus the sine of theta. And again, same thing. Replace that r and theta with x and y. So we're trying to do some similar stuff. It's just a little bit uglier than some of the ones that we've dealt with, but we have some choices. We can move some stuff around. In this case, I'm going to deal with some of the pieces kind of at different stages. So you'll see what I mean as we go through this problem. And again, the way that I'm showing you is just one way. There are certainly other ways to do this exact same problem. So I'm just going to multiply both sides by this term that shows up here in the denominator. I would much rather not have a fraction if at all possible. So I'm going to multiply both sides of my equation by 1 plus sine of theta to just get rid of the fractions. Let me give myself some room, and I will wind up with, on this side, r times 1 plus the sine of theta is equal to just 1. All I've done is multiply again by 1 plus sine of theta. And that leaves me on this side with r plus, as I distribute through, r sine of theta equals 1. So I've got 2 pieces now on the left that I need to convert. This one is great. It's ready to go. R sine of theta, we already know that that is equal to y. But this one has r just by itself. So what I'm going to do is convert the part that's ready to go and leave the other part still in terms of r. So my next line, I'm going to rewrite this r's not changing. The r is still r. But I'm going to rewrite this r sine of theta as just y. And that's equal to 1. And now I'm going to isolate the r on one side. So I've got r equals 1 minus y. Okay, so now we need to deal with this r over here. And I would really want, we want r squared, not r. There's a couple of different ways we could make this an r squared. One would be multiplying both sides of the equation by r. If I multiplied by r, I'd have r squared over here. But on the other side, I would now have introduced an extra factor of r, and I'd be back to the same problem that I was just dealing with. I'd have r minus ry. I'd have to figure out how to convert the r that was sitting here. So I don't want to just multiply both sides by r. The other thing I can do to convert this side to r squared is to square this side. And similarly, if I square this side, I'm in good shape because I'm not introducing a new factor of r suddenly over here. So that's the approach that I'm going to take. I'm going to square both sides. And I'll get r squared on this side, and on this side I will get 1 minus y squared. And now I'm to a position where this r squared term is very easy to convert. That r squared is just x squared plus y squared, and I have that equal to 1 minus y, whole thing quantity squared. We can simplify a little bit if I actually FOIL out the right-hand side and do a little bit of simplification. Leave that problem right there so we can see the whole thing. So that's what I'm going to do. I'm going to leave this side untouched, and I'm going to FOIL out the other side. I'm going to get 1 minus 2y plus y squared if we FOIL that all out. And I can immediately cancel. I've got a y squared on this side, and I've got a y squared on this side. I can subtract that term off and cancel it. And now, instead of having y showing up in 1, 2, 3 separate places, it only shows up in one place. And we're going to be able to fairly easily solve for y and get an explicit form. So that's what I'm going to do. I'm going to solve for y now. So I've got, just write what we've got. X squared equals 1 minus 2y. And let's solve now for y. I'm going to move the 1 over, so I'll have x squared minus 1 equals negative 2y. Divide both sides by negative 2, and we will get that y is equal to x squared minus 1 over negative 2, or if we want to write that hopefully a little nicer, I could write that as 1 minus x squared over positive 2. And that would be my answer. Okay, hopefully this gives you a good sense of kind of how you can work with some of these problems, and we'll look at some more kind of similar related problems in the next section where we're really going to focus on graphing.